today we're going to finish up all of the asteroids. We're going to talk about comets, but mostly today I think we're going to deal with how to avoid getting splattered by one of these things that's moving around. And there's all sorts of interesting proposals, and they all have their pluses and minuses. And I think that that's going to be really fun to go through. The power behind a lot of these impacts is hard to imagine too. So I want to try to give you guys a picture for how big of a threat these actually are. And what's really cool is it seems like we've done a really good job of tracking these really just in the last 10, 15 years. So there's been a lot of hope surfacing, and we'll get there. I do want to say, I want to just finish up the discussion about the mining of resources really quickly and talk about, just briefly about the legislation that's been going on. It seems like we've really, in recent times, we've passed a lot of legislation, at least in our country, to privatize this industry and open up the channels for people to develop space. I think this is a huge topic. If anybody here is going into political science or has aspirations of getting into politics, first of all, God bless you. That seems like a horrible career to me, but I think that young people like you really do need to get involved and change things. If not, it's going to end up, traditionally scientists have not found their way into politics. It's usually dominated by industrial types, and so it would be really wise for folks to get involved as much as they can. So what happened was, in '67, when all this moon exploration was going on, there was an international treaty that was passed, and we talked a little bit about this when we talked about the moon. It was called the Outer Space Treaty, and it was ratified by 96 different nations and signed on by I think 27 other states. And it really seemed like an optimistic outlook. So, they agreed that all of outer space would belong to the province of mankind, and that the nations would have the freedom to use and explore outer space, but they must be done in a way to benefit all of mankind, which is, I think, a really solid outlook. But that seems to have degenerated a little bit since then, which is why I think that it's really important for us to consider how we might deal with that better in the future. So President Obama signed into effect this declaration, which recognized that the U.S., it recognized the rights of U.S. citizens to own space resources which they obtained, and encouraged the commercial exploitation and utilization of spacecraft and resources from asteroids and so forth. A little quote from that piece of legislation says, a United States citizen engaged in commercial recovery of an asteroid resource or a space resource under this chapter shall be entitled to any asteroid resource or space resource obtained, including to possess, own, that's interesting, owning a space, an entire space body, transport, use, or sell the asteroid or space resource obtained in accordance with applicable law, including international obligations of the United States. And then this momentum sort of carried on forward into the Trump administration. Trump signed this executive order on encouraging international support for the recovery and use of space resources, which essentially said Americans have the right to engage in commercial exploration, recovery, and use of outer space resources. The U.S. does not view space as a global commons, which is rather interesting, and the U.S. formally opposes the moon agreements. So things have changed since the 60s. And it seems like the development of the moon is happening under our feet to some extent, right? It's going to turn into one of those situations where the frog gets slowly boiled. So I really encourage everyone to consider that when looking out at the future. I do believe that it's really important to take care of the planet, But this is going to happen whether you like it or not. It's something worth paying attention to. Climate seems to get the majority of the attention right now, and that's, I think everyone's heart's in the right place with that. But the moon is going to be developed in the next couple decades, for sure. And so we don't want to see any Star Wars happen. It's probably something that we should be discussing regularly. Questions about that? All right. Let's talk, let's finish up this asteroid discussion. I wanted to mention one in particular really interesting case, which I think hopefully someone's going to do their final project on this. Oh, I forgot to mention the final projects. One more thing I wanted to say about those. When are the final projects due? Saturday, yes. So I wasn't totally clear about this. I want you guys to really go deep with these. Try to use the entire 10 minutes of that video if you can. You have a 10-minute upload. A few people uploaded them early, and they did kind of short videos, and I think I emailed all those people and was like, hey, develop this a little bit deeper. And I think that that's really important because 10 minutes is barely enough time to get deep into anything. We do 2 of these hour-and-a-half lectures every week, and I feel like I can't even get into anything because it's so short. So 10 minutes is nothing. You guys can handle that for sure. Oh, by the way, Theodore, you were absolutely right about this record setting with the moon, the Artemis mission. You mentioned that last time, yeah. So it's an interesting little record, though. It's like the record for the farthest distance of a potentially manned spacecraft. So it's not manned. But there you go. It's funny how they gotta make our records up where we can, I guess. Yeah, next time. Well, yeah, I think we're gonna do a robotic landing next time. But Artemis 3 will be there on the moon. It's all gonna happen under our feet. It doesn't seem like people are paying too much attention to it. Anyways, back to asteroids. So I'm gonna turn down these lights a little bit. I feel like you guys can't really see too well. This is maybe my favorite space object. Turn that down just a little bit. Okay, so this is a really strange object. This is the first bona fide interstellar object that humans have witnessed in the modern, well, probably ever, but certainly in the modern technological era, which was very startling for a number of reasons. Almost everything is shocking about this object, which starting with its trajectory into and around the sun. So came into the sun, towards the sun, like many, comets. We'll talk about comets later. They often have these very highly eccentric elliptical orbits. But this one was very strange. It took this really like almost 90-degree turn at the sun, and people were this is why it caught the attention. There's actually since this discovery been one other interstellar object that's been seen, but what people noted is that the hook, the angle of this was so great that it couldn't have essentially come from within our solar system, right? It had so much velocity that it was going to leave the solar system. It had come from outside the solar system. And, just to give you a sense, normally when a body comes in, it has this elliptical orbit. Most of the bodies, most of the comets and stuff have this elliptical orbit. If a body has what we call a hyperbolic orbit, that means that as it leaves, the velocity is going to be so great that it's going to escape the system. And so hyperbolic orbits are associated with escape velocities. So often when we do this slingshot technique with spacecraft, they're going to take hyperbolic trajectories because they want to have that escape velocity so they don't get stuck in orbit around something. And this strange asteroid-y thing, sometimes called a comet, sometimes called an asteroid. They can't figure out what it is. It's very strange. It has a really high reflectivity, like 10 times greater than the nucleus of any comet that we're aware of, which is very strange. But it doesn't seem to be outgassing anything. So another thing they discovered, which is very, very strange, was that the velocity that it had when it left the sun was greater than the gravitational acceleration. So something was pushing it forward. And initially, people figured, okay, well, it's probably heating up, and there's probably some gas that's evaporating off of it and pushing it, giving that extra kick. But this became increasingly untenable. So they couldn't find these gas tails that they expected to see. And there's another thing. The outgassing generally causes a body to spin with some predictable motion, and they didn't see any of that. So very strange. It also has this, if you look at, this is a drawing of it, but it has a very strange kind of cigar-like shape to it. I mean, this is like the weirdest thing that humans have ever seen in the sky, for sure. It's very weird. And it appeared to be kind of tumbling through the sky. So they still can't explain this change in velocity that occurred, which is very strange. And, there's almost certainly a natural mechanism for this, but we don't have it. And so that led to all sorts of speculation that it was, an alien space drone or something crazy like that, which was very, very unpopular, obviously. Nobody wants to consider that we're being spied on by aliens. However, this gentleman, Avi Loeb, who I've mentioned before, who's a really interesting guy, actually was the chair. He's the longest standing chair. I don't think he's the chair anymore, but he was the longest standing chair of the Harvard Astrophysics Department. And so when a guy who's really credentialed like this starts advocating for something as crazy as an alien origin of this body, people start to take it seriously. And so if you're interested in this, I really recommend that you check out Avi. He's all over the internet. He's all over YouTube. We had him on our podcast too. And he's just a really smart guy who can put complex mathematical ideas into really succinct points. I love his mathematical explanations because they always boil down to very simple high school algebra and so forth. It is, yeah. And people have, there's been some folks toying with the idea of going to chase after it. Nothing scheduled for launch or anything like that, but it is possible that we could catch up with it. Yeah, I don't know. I mean, nothing's funded, so probably nothing will happen. But I think I think people will be looking out for these things in the future. And so potentially, if we had been all right, this is particularly crazy because, when I was in college, well, really even way after that, when I was in grad school, nobody believed that the solar system contained anything from other solar systems, right? This is a huge paradigm shift, right? Everything that, like I said, I keep beating on this dead horse, which is that everything we've dated from our solar system dates to 4.5 billion years ago, which has historically been thought of as the origin date for everything here. I personally believe that proposal is becoming less and less tenable because, of course, these dating methods can only reflect the last time that everything got melted on the surface. And so this was reinforced by the idea that all of the meteors that were striking the Earth were from the initial moments, or were formed, essentially, at the same time as the solar system. That doesn't seem to be a reasonable proposal anymore now that we're seeing interstellar objects. And there have been, I don't want to say 3, but I know of at least 2 that have collided, small meteors from interstellar origin that have collided with the Earth. And actually, Avi is going this winter out to try to dig one up from the bottom of the ocean. There's actually going to be a Netflix special about this too, if you want to watch it. We tried really hard to get Avi to let us come with him out there and film it, but Netflix beat us to the punch, of course. And actually, to be fair, a lot of people are really pissed off at Avi because they're like, hey man, no matter what you dig up from the bottom of the ocean, you're going to say it's your meteor. because there's probably all sorts of meteors at the bottom of the ocean. And so, a lot of the astronomy community really hates this guy. So that's worth mentioning. They think he's very, very cavalier with his interpretations. And fair enough, but it is this Oumuamua object is extremely weird. No matter what it ends up being, it's a very, very strange object. Even the shape of it is very strange. We don't see anything like that, even remotely like that, actually. So it's a weird one. It's worth keeping an eye on. But let's talk about the ones that are, in general, smashing into us, because they're happening quite often, and some of them are quite large. This is a map over the course of, 1994 to 2013, so, roughly a couple decades. And just to give you a sense of scale, so we have, you can see these little dots, and the dots correspond to the amount of energy that's being blown off. So the big circles, the biggish ones, not the biggest, but the ones second to your right over here, 100,000 gigajoules is about 1.5 times the power of the Hiroshima bomb. Okay, so, and these have happened in our lifetime for the most part. Oh, I don't know when you guys were born, but yeah. So this is happening all the time. The thing is that these explosions usually occur either over the ocean or in unpopulated areas, so we don't hear much about them. There have been a few that we'll take a look at. Well, yeah, there's been 2 big ones in modern-ish times. Both of them in Russia, actually, come to think of it. I've got a video of one of those in a second that we'll watch, which is pretty crazy. There was also this event where a comet broke up around Jupiter that we've mentioned before, which really, this is in the 90s, and really changed people's tune about the risk level with these matters and started the entire project of cataloging the near-Earth objects and getting to the bottom of it. And of course, like I said, the whole Chicxulub event for the extinction of the dinosaurs really came into its own in the 2010s. And so this started to be considered a very serious problem. So the comet that smashed into Jupiter had a power of 6 million megatons of TNT. And just for reference, that's 6 trillion tons of TNT, whereas you only had 32,000 for Hiroshima. I mean, this is a freaking huge explosion. The one that smashed into Chicxulub was about 100 million megatons of TNT, so actually bigger than the Jupiter one, but not by much. And that's in recent history, right? And if we can go back and try to remember when we were studying the Earth and we were talking about mass extinctions due to impact events. Several of them are hypothesized to be due to impact events. And they happened with a regularity which is putting us sort of right in the nice pocket of being due for one of these things. And I mean due within the next, 100,000 years or so. So we have some time. So it's good that we're starting to take a look at these possibilities. Let me see here if I can start this. I might have to do it from the computer. Oh, there we go. Okay, so we have some explosions, so you get the idea of it. These are small explosions, right? These are, of course, nuclear bomb tests and things like that. These are millions of times less powerful than the events that people are looking at in terms of the ones that we're watching out for. So I really want you to get a sense of if an atomic bomb is only 1.5 those events that we saw are some of those bigger events in the last few decades are on the order of these atomic bombs. And the ones that took out the dinosaurs are millions of times worse than that. It's a pretty serious threat to us, and it's something that I don't think that we can, there's no paucity of effort that can be spent on studying these kind of events. Let's see here. So by the mid-2010s, it looks like we've accounted for, and I don't think that this registry has been updated since then, that I could find, but it seems like we accounted for about 90% of the near-Earth objects, which are bigger on the order of a kilometer in size, right? So the one that smashed into the Earth in the Yucatan Peninsula and took out the dinosaurs and most everything else on Earth at the time was on a 100-kilometer sized object, right? Anything bigger than a kilometer would really mess us up badly. I think that it definitely has the ability to maybe not end life as we know it, but certainly disrupt things to the extent that we would have difficulty maintaining our electronic global communication and things like that. So that's 100 times less. I mean, these are fairly common events, and we're doing everything we can to remedy that. All right, so this is the Chelyabinsk. So in 2013, there was this little-ish one. This guy was actually only about 20 meters in diameter. Let's look at a picture. Let's look at a movie of it. It's always very difficult for me to control this screen over here. Come on. So this thing had an explosion that was about 30 times the explosion. Ooh. I don't know how to turn off the sound. Good God. Okay, we don't need to hear the explosion. You get the idea. All right, so this thing had about 500 kilotons of energy, and this is something, like I said, it's about 30 times the size of the nuclear bombs that hit Japan. Fortunately, it didn't actually kill anybody. It occurred in a relatively not densely populated region, although the shockwave from it blew out all the windows in the area. And that was enough to send something like 1,500 people to the hospital from glass injuries from this thing happening. So, these things do happen. This was obviously too small to be detected. I mean, this is only 20 meters in diameter. And when we say we've accounted for 90% of the near-Earth objects, we're talking about ones that are bigger than a kilometer, right? So what is that? That's something like 500 times bigger. So things can be dangerous even if they're not big enough to end the civilization. This is certainly enough energy to cause a great deal of harm if it were to happen over a big urban center like Manhattan or Portland or something like that. All right, so there was another one, which was perhaps a little bit more famous and certainly much bigger. This one was actually thought to be about 60 meters in diameter, which is still a far cry from dinosaur-ending collision. But this happened in a remote part of Siberia, near the Tunguska River. It's often referred to as the Tunguska event. But the blast was big enough to take out an entire city. And this is well before people were tracking these things. But it's, again, worth pointing out, 60 meters in diameter is way less than the size of something that NASA is trying to track with these things. So, I think in terms of funding, this is probably something that we should try to figure out, is how to track the things that are orders of magnitude smaller than the ones that we're actually screening for. course, it's not going to be a world-ending event, but if an impact were to happen over a city, I think that would be something that humans have not even witnessed, really, right? These are much stronger than the Hiroshima bombs, and of course, some of the urban centers that we have today, they absolutely, they're much, much bigger cities, right? Hiroshima was a terrible tragedy, Nagasaki, but these events have the potential to take out much, much, much bigger populations. And what's really strange about this Tunguska event is that it doesn't appear that there's any kind of an impact crater. So it seems like it blew up in the atmosphere. And they've never been able to really find the remnants of this and so forth, which is very strange because, while it's recorded as the largest impact event, there's no direct evidence that it was an impact event. And so there's been a number of detractors over the years. Particularly one gentleman, an astrophysicist named Wolfgang Kundt, made this proposal, which I think is reasonable, that there was some sort of leakage of volatile explosive gases from some pocket inside the Earth, actually, and that it wasn't an impact event at all, but there was some sort of jet, some sort of leakage, and that it was ignited by something like a lightning bolt. And there are some really interesting disaster, well, it's horrible to call disaster interesting. There's been some really tragic events where blobs of gas have actually emerged from the bottoms of lakes. Particularly, there's a couple I recall reading about. There was one recently in Africa. There's a lake that belched out some gas, and I think that this one was primarily carbon monoxide. I'm not sure if there was methane in that. Methane would, of course, be ignitable. But this was tragic because the gas rolled downhill and basically suffocated an entire village while they were sleeping because it was heavier than air. So we know these kind of things do happen, strange things like that. And yeah, the Tunguska event is something of a mystery, and I think it will remain a mystery unless someone finds some traces of something that resemble an asteroid. Very, very, very strange. People tried to blame it on Tesla too, which is really interesting. He was doing these wireless energy transfer experiments around the same time at his laboratory in Weidencliff in New Jersey. And so there was a number of, at the time, there was a number of conspiracy theories that it was Tesla's fault, which no doubt did not help his public image at the time. Real tragic figure, that guy. Okay. So let's talk about how to avoid these things. The thought is that anything on the order, like I said, of a kilometer would not only cause local damage, but it would disrupt the infrastructure in the surrounding region. Things below a kilometer are not thought to be world-ending events. So obviously the priority is on stemming the world-ending events. But it could be pretty bad. So let's see, as of 2009, we had basically narrowed this down to 2 to 3 kilometer objects. And then since then, we've been cataloging the 1 kilometer events. There's a number of countries working on this project, and overall, all of the countries are contributing to the same database, which they call the Space Guard program, which is something to keep an eye on. It looks like the program essentially has figured that they can spend as little as $250 million and wrap up this project by 2028. I'm not sure exactly where they're at in that process, but it seems doable. And of course, after that point, once we're tracking all of these things, by the way, this is a picture of all of them. There's quite a few you can see there. And so we'll probably, God willing, have time to get around to the little objects before they can cause us too much of a headache. Now, when we talk about deflecting or destroying these things, there's a number of trade-offs with respect to overall performance, like how well it's going to work, how much it costs, what is the potential new problems that you introduce by interacting with these, because that seems to be really the main concern, is that you make things worse on yourself. And then also, who's in control of the power to deflect these, right? So we'll talk about that later, but there's some thought that the technology that could be used, the same technology that could be used to save us from these, could also be used to turn them into weapons, right? Because when you can drive an asteroid around, you can crash it into somebody too. And with, deteriorating cooperation between the mega states, this is an increasingly real threat. So there's a few different, you can broadly break these strategies up into two things. One is fragmentation, right? Blow it up, basically. The other one is to delay the impact. So, it's worth considering that the Earth is something like 12,000 kilometers in diameter, and it's cruising through space at about 30 kilometers per second. So that means that it covers an entire length of itself in about 7 minutes, which means that you don't have to push them very hard to get them out of the way. And that's, to some extent, this is the major strategy. However, it's a lot easier to blow things up. So when it comes to how much time do we have to, and we also have plenty of blowing things up technology already in place to use on each other. And so the community is often very split between, on one hand, people are always coming up with new strategies of how to deflect these, and then the military is always stepping up and being like, no, we got this, it's fine, we'll just blow it up. And yeah, we'll talk about some of the pluses and minuses of those here. So this is an interest. So the direct methods, it costs less. They can be done quicker. The problem is that a lot of the asteroids be something like rubble piles, right? They seem like if you were to explode a bomb next to them, it wouldn't necessarily just push them away. It might make, let's say, 500 problems where you used to have one. And at that point, it's going to be very difficult to track down and snipe off all of those little, well, not that low, right? We saw what a several meter-sized object can be a pretty serious problem. And it's worth mentioning too. And next week's textbook will walk you through some of this. But almost all of the meteor showers that you see, have you guys seen meteor showers? You've seen shooting stars and stuff, right? Those are like little pieces of dirt, basically. They're tiny, tiny little things, right? Those are usually the reason these are predictable is because the Earth crosses the stream of some sort of comet, and there's just all these little dust and maybe pebble-sized at most objects. So these are nothing, and they still light up the sky quite a bit. So the idea of blowing one of these things up near us might create a bigger headache than the one, well, not necessarily a bigger headache, but a new problems. So things that I think are really exciting are the delay strategy events. The problem with the delay strategy events is that you have to basically have that technology on hand ahead of time, right? You need to have a program in place that's developing these projects, because oftentimes they require you not only to know where it is, but get out there in time. And as we've seen with something like the Artemis program, it can take decades to develop a launch program that's capable of reliably getting to some place and actually interacting with it. So these are like forward-thinking strategies, and unfortunately humans are pretty bad at those. We want to spend money on things that are going to affect us today rather than the things that might be a problem 20 years from now. So I think they're worth attention. This one that I have on the screen right now is a device called a gravity tractor, which is weird. But the idea is basically that you put something in orbit around it that pulls the body slightly out of the way, right? And of course, the further away you detect these things, the less you have to change the trajectory. And though it's potentially a really clean avoidance strategy, but it requires a lot of foresight. In fact, more foresight, the better. There's some ideas of using explosive technology as a delay means by essentially deflecting it. But this requires very careful calculation of how close you are to the object. You also have to know the composition of it, right? Because you don't want it to fragment as you go. And so there are explosive strategies embedded in these delay type tactics. So let's see. we did actually in 2005. We talked we talked about the DART mission, but we didn't talk about the Deep Impact mission. And this was kind of interesting. So the Deep Impact mission, the probe was sent out to visit this comet, which was called Tempel 1, and smashed into it. And it seemed like we didn't really change the comet's orbit, but it did deflect it a small amount, right? And so this was promising. It wasn't enough of a deflection. I think that the amount of force that we delivered to that object, it was something like 5 tons of TNT, which is nothing compared to any of the that we've looked at just now. And actually, I couldn't find any indication of how much we changed the orbit of this thing. So it was very much a pilot study where we were just trying to see if we could get to somewhere and bump into it. The idea, though, is that if you were able to get out there and put something really explosive slightly above it or drill into it a little bit, you could actually change the orbit appreciably. You know, there's serious concerns with sticking a nuclear weapon on the top of a rocket and launching it, right? Have you guys seen some of these fail tests of the SpaceX rockets and stuff, right? They're very reliable, but every once in a while they come right back upon us. And even if they didn't detonate, you would still be, you'd have nuclear material strewn across the desert or wherever, which would just be a nightmare for future generations to clean up. You know, there's also this thought that even if you took a nuclear bomb and you exploded it a little bit, not really even next to it, but somewhat in the proximity, that the radiation given off by that explosion would be sufficient. The X-rays and neutrons that were released would be sufficient to push the thing away. Problem is, these are all essentially calculations, right? Nobody's actually testing this idea. Nobody's rushing to start blowing up nukes in space, for better or for worse. And so, you know, while they are sort of cheap options, they're going to be very untested. And if we do have to implement one, it's going to be one of those things where the experiment is the actual final, the final performance at the same time. So, yeah, not a huge fan of these explosion ones personally. Let's see. So just to give you an idea of the design, this is a proposal that came out of Iowa State in 2011. And he's basically proposed this probe that essentially has this big, long scaffold that extends out ahead of it. And the idea is that the scaffold has some small explosive on it, and it touches the asteroid right before the main body of it touches it. And when it forms a little crater, basically, so that when the back end of the spacecraft hits into the asteroid, there's like a little divot. And at that point, you can do a number of things. You can blow it up. You can actually maybe even stick a rocket thruster there, which is kind of interesting. And in some ways, drive the asteroid. I actually think this is probably the method that people will end up using in the future, is something where they steer these things around with thrusters that they bring out.
I was confused because I thought Lindsay connecting factor out of this source has been kind of like hit baseball.
I mean, it's a rough proposal, right? So I think there's a lot to be worked out. I didn't read this actual paper itself, but I watched some videos of the proposed technique. And it, of course they're proposing that they'll have great control over it, but that remains to be seen. I think at the very end here, we're going to talk about the visit that we made to one of these comets with a lander. And one of the things that happened that was completely unexpected was the thing essentially, I don't want to say tumbled, but it found its way into a little cranny, and we lost communication with the thing. So, burying a probe inside of an asteroid has its own host of problems, right? Burying thrusters as well that you're hoping to control is not going to be an easy task for sure. And yeah, you could end up with you could very easily imagine all sorts of things going wrong with this, right? Steering the thing like directly into Manhattan or something on accident. And there's a lot of politics about that too, right? Because inevitably, when you talk about steering something, you're going to be steering it away from your city centers, but maybe you don't have the ability to steer it away from all of the Earth, and so you're going to be looking for a place to smash it into, and who's going to get hit with that? Somebody, maybe. Especially with the sub-kilometer type objects, right? So there's some interesting geopolitical concerns about who's going to eat the asteroid if we can't actually get it completely out of our way. So yeah, I think that in the deep future, the best proposal is that we can really manipulate them. We can really actually attach, it sounds absolutely crazy, but that we can attach some sort of ion thrusters to them and do some super sci-fi maneuvers and drive these things around. Not without its own problems, of course. Now, there's a couple other kind of interesting proposals that are contactless aversion strategies. And one of those is this thing I have on the screen. It's called an ion beam shepherd, which is a pretty cool sounding name. The idea is basically that you basically take a thruster from like a satellite and point it at it, sort of like the exhaust of a spaceship, and you just sort of blow it away, which is an interesting idea. Another idea is putting like a solar sail up in front of it. And these things are being pushed around by the solar wind, and the idea is that if you could manipulate that stream of solar wind, you could get these things out of the way that way, using some sort of mirrors or reflective devices. And this is actually thought to be a pretty fast way of doing it. There's NASA. It seems like the NASA website says this is achievable within a year, which is pretty wild. So it's something we could use, maybe an alternative to bombs, which I like a lot. There's this other idea, which is pretty crazy, which is essentially using something like a railgun. I don't know if you guys have seen anybody seen The Expanse? It's a good one, right? They love the railgun in The Expanse. But the idea is basically that you just have a big, long catapult, and you throw objects at it from the Earth or maybe from the moon or something like that, which is pretty cool because shooting something using propellants is extraordinarily expensive. Again, that's, I think, what the majority of the time spent on these missions when we talk about the Artemis mission or any mission that's trying to get a craft into space. Almost all of the development time concerns how to get the package into orbit. It's very, very expensive. Building these robust rocket propulsion systems is tricky. It's volatile. They have the potential to fall over and blow up. And so these railgun things are actually a pretty exciting idea, I think, in terms of alternatives to shooting rockets. There's also the idea that we could perhaps use a laser. And I think these are actually probably pretty good ideas for globally unifying projects for the moon bases as well. You know, the moon doesn't have much of an atmosphere, hardly any atmosphere at all. The gravity is not that bad. It's potentially a place where we could situate some of these protection devices. But yeah, with the laser, it's thought that you could basically flash a blade or vaporize some of the material on the surface of these things, some of the icy material, and that outgassing would steer them off of course. A couple of other runner-up ideas. Painting it with something reflective, like titanium dioxide. It's a pretty cool idea. Releasing a cloud of vapor in front of it is another idea called cometary aerobraking, which is pretty cool. Oh, I guess cometary aerobraking is actually when you target another comet that's in the vicinity and try to break it up even further to deflect it. Again, I don't know. That seems like it could make more problems than the original. Another one would be attaching a big ball and tether to it, like a big ball and chain, and swinging its orbit out of place. And then there's a couple of magnetic proposals, which are pretty crazy. This would work with something that, like an iron meteorite that's potentially magnetically interactive. And you could basically take a spacecraft out there and build one of those solenoids like we talked about at the beginning of this series and deflect it electromagnetically. That's a pretty cool idea. You know, the OG of science communication, Carl Sagan, wrote a chapter in his book, Pale Blue Dot, which is a great book. You should all read it, where he's very, very concerned about the genocidal potential of bureaucracies on Earth abusing these technologies. You know, it's true, bureaucracies are strange, they're very effective, but they don't have human hearts always. And so, you know, if somebody thinks that another state is a threat, it's very easy to turn against them and make these sort of heartless decisions. And so once this technology is in place, there's no guarantee that it won't be abused by somebody. And so Sagan elaborates on that in his book, and it's a little, it makes you feel a little uneasy to read his ideas about that. Still, I recommend that you do it. So, yeah, that's where we're at, I think, with all of this. Does anybody have any thoughts or comments about asteroid deflection? It's a lot, yeah. I think there's been a number of movies about this.
Yeah, that was probably not the best way. Like, what do we do when there's one that's
Yeah, same thing. Hopefully see it way in advance, right? Actually, we're going to switch over and talk about comets here for the back 20 minutes of class. Comets are actually potentially a bigger problem because they tend to be bigger than asteroids. Most of the big asteroids, remember, what is an asteroid? It's basically a planet, okay? I mean, it can be a little planet, fair enough. But, you know, we looked at Ceres last time, it's basically a planet. And most of those big planetoid-looking asteroids are out there in the asteroid belt, fairly securely fastened to their nice, predictable orbits. So the comets, on the other hand, which we're about to get into, are a bit different, right? The comets have these really long orbits. There's two different kinds of comets. There's ones that have short orbits, but even the short orbits are like 200 years, right? So you don't really see them. And there's another really interesting thing about comets is we always think about comets as having these beautiful tails, you know, oh, we'll see it coming from far away. Well, they don't have the big tails until they get pretty close to the sun, as it turns out. So, and we'll show an interesting example of this because we flew out to one of them and, we were getting all these great images of it and so forth, but once it started to approach the sun, the spacecraft had to kind of back off from it because it started shooting all this gas out of it. And I think this was, I don't know if it was surprising, but it certainly wasn't part of the plan originally. And so the idea that you can see comets coming in is a bit misleading, although they're obviously quite visible. Any other thoughts about asteroid deflection? All right. So what is a comet? And how does a comet differ from an asteroid? Well, so historically, we think about comets as being icy. This line is getting pretty blurred, though, lately. There's paradigm shifts underway. But, you know, particularly since Ceres has these nice jets that are popping out of it, and it turns out to be quite an icy body. And actually, a number of these meteors out in the belt are seeming to be not so different than comets in composition. And so I think that it's actually probably more accurate to think of a comet as a type of meteor. One that has a really elliptical orbit that spends a lot of time in the outer reaches of the solar system and then periodically comes in. They all tend to be very icy, which is why they have these particular appearances. And we'll talk about their composition here in a moment. But you know, comets have a really interesting historical story. They're very visible. Has anybody seen a comet, by the way? Anybody see that one that happened a couple of years ago? Yeah, you saw it? Some binoculars? Yeah, I saw it too. It was pretty hard to see, though. I had to get up. I was living in Portland at the time and had to get up on a big hill with some binoculars, and it was kind of like, I think that's it. Yeah, it looked like a cloud, basically. But some of the bigger ones, you know, when I was a kid, there was the Hale-Bopp comet, which was extremely visible in certain portions of the United States. So historically, they've been the most visible bodies in outer space, and historically, people have freaked out about them and usually ascribed terrible, you know, they tell of terrible things to come, right? So it seems like the basis of treating them as bodies in the solar system is relatively modern idea. So as early as 1st century AD, the Romans were treating them like these humanoid objects, right? They thought they were these like bearded gods, essentially. And this was the idea that was carried on for centuries afterwards. Again, there's a lot of confusion between comets and meteors, right? Remember, meteors only last for a few seconds, right? We see these meteor showers. They're usually these tiny little grains of dust or pebbles. Comets last for, you know, a long time, maybe weeks, and they stay in the same part of the sky. So they're very different, and you don't want to get those two confused. It seems like around the globe, people were starting to come up with astronomical ideas for these. So India was one of the first, actually. It seems like there's some writings by different astronomers in the Vedic tradition that had the names, and they estimated the periods of some of these comets, but they didn't show their work, so people don't exactly know how they came up with them, and they can't, again, since these things happen sometimes on the order of hundreds, sometimes thousands of years, especially the long period ones, they haven't been able to verify these. But there's some thought that the Indians were on top of this as early as the 6th century. Newton, could Newton just have not done one more thing? It's kind of annoying how much Newton cleaned up for physics and astronomy. But Newton was really the first person who came along. Of course, Newton came up with the basic idea of gravity, which is, you know, still an incomplete idea, but essentially had this idea that the bodies were pulling on one another. And he used his inverse square law to trace out these. This is actually a picture from his Principia, which is his magnum opus. And he was able to show how a comet's path was essentially following a parabolic orbit as a result of this inverse square law with gravity. And this, he used the comet of 1680 as an example. A bit later, this gentleman, Edmund Halley, who we all know from the Halley's Comet, came along. And he did the fine work of applying Newton's math to something like 23 different cometary type events that happened over the course of his lifetime. it seems like three of them, this is also quite interesting, three of the bodies that he was watching seemed to have deviations from their orbit, which he actually ascribed correctly to the influence of Jupiter, which is rather astute. And we'll talk about how actually the fate of a lot of comets lies in big bodies like Jupiter, the gas giants, which tend to sweep these things up. And there's an interesting, this idea that the comets are getting chewed up continually too, but that their rate of appearance doesn't seem to be depreciating, indicates that there's new ones being not necessarily formed, but there's a reservoir of these comets somewhere. And that's actually how we ended up with the idea of the Oort cloud, which we'll finish with today. So Halley kind of made this a real science. And people started to really start to think about what these things could have been made of. The natural philosopher Immanuel Kant was the first person who really considered that they could be, really considered their composition and considered that they're basically, this stream is basically vaporized material. I forgot to mention, but before Newton, people were thinking that they might be an atmospheric phenomena, right? They might be something happening up in our upper atmosphere, sort of like sprites or some sort of lightning, some sort of electromagnetic thing. But this gentleman, Kant, and Kant's a philosopher too, which is strange, but people were doing a little bit of everything back then. Nobody was just an astronomer, right? You're always like an astronomer and a doctor and a philosopher and like everything else. It's kind of crazy. Different times. So then this gentleman, Friedrich Bessel, came along and came up with this idea that the jets that were being evaporated off the surface would actually explain some of the perturbations that they couldn't explain with Jupiter, and that was pretty cool. But then it seems like the research sort of stagnated until the mid-20th century when this gentleman named Fred Whipple came along and really dialed in the composition of these. And he coined the idea of dirty snowball, which is kind of stuck up to the moment today, although some people call them snowy dirt balls as well, because they seem to vary depending on their composition. So you can have one of either, but essentially the comets turned out to be exactly that. They're these very icy chunks of debris, which is quite interesting. And again, like with the exploration of Ceres, the lines becoming more and more blurred between comets and asteroids. So let's look at them a little bit. So when you look at a comet, and I really hope everybody has a chance to see one in your lifetime, they have actually two tails on them, which is rather interesting. One of the tails is left behind in its wake, which is this debris tail that sort of more closely mirrors its path that it's been coming through, right? These are the heavier pieces of dust and so forth that are blown off of it. And then there's this ionized tail of it, which really reflects its orientation with respect to the sun as the volatile gases and so forth are getting ionized right there. They're interacting with the solar wind. And this was actually a really important note by people around the time that the concept of the solar wind was being developed. And we're going to talk a ton about the solar wind next semester. But it's a really fascinating phenomena that seems to dictate a lot of the stability and a lot of the processes that we're going to have to face in our own space exploration. So studying comets was really how we came up with the idea of the solar wind in the first place. That's pretty cool. There's been all sorts of, so what's really strange is the gases that are given off seem to be often quite complex. So you see organic molecules, which is really interesting. I think that this has given a lot of wind in the sails of the panspermists who are arguing that life maybe came from another place altogether. I don't want to say they've found, but there's at least been a report, a NASA study that indicated that DNA and RNA components like your AGTC type molecules may actually form inside of comets and asteroids. Their conditions are appropriate anyways, although I don't believe that we've plucked any out. So that's kind of fascinating. And of course, some of these volatile molecules, everything from methanol to cyanide, formaldehyde, ethanol, hydrocarbons, they're just very rich, fertile, organically fertile balls that appear to come from the outer reaches of the solar system. And, it's worth mentioning that the idea of where these things come from, the reservoirs, there's essentially two places. The short-lived ones are thought to originate in this field of debris out there in the trans-Neptune region in the Kuiper Belt. And then there's this really far-off one called the Oort cloud for the long-period comets. And the development of the idea of the Oort cloud is very nascent. We know very little about it. But it seems like the paradigm is moving more towards the idea that often the objects that are out in the Oort cloud may have been derived from other solar systems altogether. The outer reach of the Oort cloud, by some measures, has been estimated to reach several light years away from the sun. And that puts it very, very close, if not overlapping, with the potential Oort cloud of other solar systems altogether. And so there might be this exchange process going on, right, where materials getting scooped up and redistributed between bodies, and especially during the formation process, which is really fascinating if you think about the building blocks of life potentially coming from other places in the galaxy altogether, coupled with our objects like Oumuamua and some of these other interstellar objects. This is such a new science. We know next to nothing about it, but it does seem like it's increasingly being considered as tenable and possible. So what else can we say about comets? The coma, right? This is the tail, the proper word for the tail of the comet. It can stretch for millions of kilometers, potentially being much larger than the sun itself. However, the little nucleus from which all this is emitted is generally limited to, at most, a few tens of kilometers, which, of course, makes it still a serious threat to us should we encounter one of these that we weren't aware of. Another thing that's kind of interesting, this will matter more next semester when we talk about trying to make sense of different sources of radiation in the galaxy and in the cosmos, is that comets were recently discovered to emit X-rays. And this was very shocking, I think, to people at the time, because generally we only think of X-rays as being emitted from really hot things. And this is still somewhat poorly understood mechanistically, but it seems like it has to do with the interaction of the comet with the sun. And so, we don't need to get too much into that, but when we start to interpret X-ray sources prove to be a really important part of how we understand the birth of stars and so forth. We have to now begin to think about comets as a potential contaminant in those projects. All right. So this was our study. I mentioned this briefly. This was the Rosetta mission. And Rosetta went out there and made this approach to this comet, which has a really boring name of 67P. This thing was about 5 kilometers across. And it spent a fair amount of time, and it got some of these beautiful images there. And I pulled this out of your textbook, actually. And what you see here is that like in figure A, which is over here, it doesn't have any sort of stream. There's no coma, right? When it's out far away, when it still hasn't come close to the sun. And then as it gets closer, the spacecraft ends up having to completely back up off of the thing because the outgassing becomes so intense. And these are just basically little subsurface chambers that are sublimating, very quickly evaporating the material and squirting it out, the volatile materials. So this was pretty cool. This is kind of by far our best picture of what a comet actually looks like. Way better than anything we took with a telescope. which is pretty cool. It's also interesting that it has like 2 lobes on it, which seems to be a not particularly unique phenomena. And people are toying with the reason for why this is, if it was the agglomeration of 2 different ones that came together, or if there's something about the way that it erodes that led to this. We don't totally know. So that's our best picture, folks. All right, so, oops. Most of the comets that we're aware of, they have these elongated elliptical orbits that only bring them in close. The periodic ones that we're actually tracking, so the ones that have orbits around 200 years or less, are considered the short period comets. And because the short period comets have this tendency for for their farthest point to coincide with the giant planet's semi-major axis, they tend to crunch into them, or at least interact with them in a way that tears them apart. And this is how the Shoemaker-Levy event we talked about with Jupiter occurred. And it's not that this happens quite often, actually. Oh, by the way, let me just explain this figure really quick. Well, hold on one second. So it's thought that the short period comets come from this body called the Centaurs, or from the Kuiper belt, which are also known as the scattered disk objects. And if you can see here in this picture, the Centaurs are those green ones, and you can see the planets labeled, the giant planets there, Jupiter, Saturn, Uranus, and Neptune are in red. And the Centaurs are sort of scattered amongst them, right? The Kuiper belts are these blue, light blue objects that are just beyond that. So almost all of these short period comets are coming from these reservoirs. The long period comets are a bit more strange, because they're actually what led us to develop the hypothesis of the Oort cloud in general. And we saw one of these, I think, for the first time in January 2007. And we saw a comet that appeared to have a period of about 92,600 years, which is fascinating. Obviously, we didn't watch it for 92,600 years. So the presence of these long period comets and the idea that somehow comets are being replenished as fast as they're getting destroyed led to this concept of the Oort cloud, which is where we are finishing our tour of the solar system today, because the Oort cloud is the absolute edge of what is known, and very little is known about the Oort cloud. I suspect that when we teach this class 10 years from now, we will have much, much more to say. But the Oort cloud, let's leave it with this. The Oort cloud might have trillions of objects larger than a kilometer, and if that is our reservoir for where we're getting these long period ones, there's plenty of things outside of our near-Earth orbit which are worth minding. So I hope to see a lot more research going into that in the future. And that's the end of the solar system, my friends. So next week, I wish you all the best of luck with your finals. We'll have a very fun last class. We're going to recap all the paradigms that we've visited, some of the mysteries that remain, and hopefully I will see you guys all again the following semester. But for now, focus on your finals, focus on getting this project in on time on Saturday. I'm going to grade them on Sunday, so don't be late. And yeah, have a great weekend. Good luck, everybody.